Okay, so welcome to lecture 5 in the finite element methods in analysis and design. My name is Andreas Andersson, and this lecture will deal with plate elements. This is obviously recorded, and you can, during the lecture, send some questions during the group chat if you want, and I will try to answer the questions either in relation to the presentation or during the breaks. Okay, so let's get started. I imagine that many of you have read about plate elements before, maybe in other courses. So here I'm going to go through some repetition of the theory and then its application to finite elements. So the outline for today is covered to a large extent in chapter 15 in the course literature. So you could see this lecture as an introduction to that chapter. For more in-depth knowledge, I suggest that you read carefully that chapter in the book. There are also a vast number of books devoted to plate theories and shell theories. One recommended reading is Plates and FEM, Surprises and Pitfalls, which you can find online, I believe, which is quite good, in my opinion. So today I'm going to go through two fundamentally different plate elements, namely the Kirchhoff and the Mindlin plate elements, which basically are thin plate theory and thick plate theory. So they have their equivalents in beam theory, where you have Orla-Bernoulli and Timoshenko beam elements. And in the end, I will give a brief introduction to Abaqus. There is an Abaqus tutorial presentation on Canvas. I think I might have a little bit time extra to go through that briefly. So we'll see in the end of this lecture. Sorry about that. So introduction. Well, generally, plate elements are planar structures with a relatively small thickness compared to the planar dimensions, and all the forces are applied perpendicular to the plane, as illustrated in the figure here. So we have out-of-plane loading, and we have a state of bending and transverse shear potentially. And throughout all of the plate theory, the normal stress in the thickness direction is neglected. So if we have a coordinate system x, y, z, z being upwards or out of the plane, the stresses in this direction is assumed to be 0. And we define the plates by its mid-surface, where we say that the z coordinate is 0. So along this plane, xy plane. So we only define the thickness, but not as a volume. There are different notations in different literature, obviously, for how to define plate elements. And here I'm mostly going to follow the course literature, but also when it comes to the theory, some of the figures and notations are taken from this book, Plates and FEM. So you can also read more in that book if you want to have an extended version of the theory. Okay, I will come back to this picture later on. So we have two different kinds. We have the thin plates and thick plates, and thin plates are based on Kirchhoff plate theory, which was developed in the mid-1800s. It's similar to Euler-Bernoulli theory for beams. So if we consider a section of a beam like this with a thickness T, in the Z direction we have the vertical displacement W, and in the x direction we have the displacement u. So if I have a thin plate, plane sections remain plane after bending and perpendicular to the mid surface. So the dashed dotted line is the mid surface, and the deformed plane is perpendicular to that. And this means that transverse shear strains are neglected. So this is the typical Euler-Bernoulli beam theory approach. If you have the thick plate theory, named Mindlin plate theory, it's similar to Timoshenko theory for beams, and this was developed, I believe, in the 1950s. So the thick plate theory, still we assume that plane sections remain plane after bending, but not necessarily perpendicular to the mid surface. So you have another slope there. And in those elements, transverse shear strains are included. So those are the fundamental differences. I'm going to go through some of the basic plate theory, not in great detail, but well, relatively as an overview, I would say, just to get the concepts of it, and then later we'll see the application to finite elements. So when it comes to the differential equations for plates, you separate those in kinematic, constitutive, and equilibrium equations, where the kinematic ones are the displacements and curvatures. The constitutive ones are section forces, and the equilibrium equations related to external forces. So if you have an example of a classic beam theory, we only have the displacement W, as we saw from the previous picture here. We have the curvature kappa, which is the second derivative, like this, of the displacement. And this is our kinematic equation. We have bending moment, which is proportional to the curvature, like this. So this is the typical, what we call the beam equation, I suppose, which is well known. And then we have the equilibrium equations, saying that the external loads are the second derivative of the bending moments. And combining this, we end up with the final expression of the beam equation, which is a fourth order differential equation, from which we solve the displacements. And if you look to thin plates, we have a system in 2 dimensions, so two-way bending. So we still have only the vertical displacement, but we have 2 curvature components and a twisting component, and 2 bending moments and a twisting moment, and still only out-of-plane vertical forces, P. So this component here, the force order partial derivative, is identified as the same as for beam theory, and we have the same in the second direction, and then we have a cross term looking like this. And here D is the plate stiffness instead of EI. So there's a great similarity in between those two. If you have a thick plate theory, we also have the additional components here due to the shear strains and shear forces, which I will come back to. So we can illustrate displacements and deformations as follows. We look in the XZ plane. Now, this particular picture is taken with a Z in the down direction, and the other, in the finite element book, it's in the upward direction. So maybe they should be flipped for illustrative purposes. Yes, I will update also this slides on Canvas after this presentation. So I made some adjustments yesterday to this presentation compared to the one that you already have on Canvas. Okay, so you have a horizontal displacement ux and out of plane displacement w, and this cross section will deform like this, and you will have some slope phi x here, and similar in the other direction, phi y. So that's an illustration of the displacements. If we then look to the moments and curvatures, we look at our slab again. We have a bending moment mx along the y direction, which causes bending like so, and then a curvature kappa xx. This is under the assumption that we have the Poisson's ratio to 0. In case we have non-zero values of the Poisson's ratio, you will have a transverse bending effect in the other direction, which you will study in part of exercise A. Similarly, in the other direction, you have a bending moment MYY and curvature kappa YY in the different direction. And finally, you have a twisting moment MXY, which causes this component rho XY. So this is the moments and curvatures. Then we go to the kinematic equations, again, which were in the very beginning. And this figure is also taken from the book. We now have the z axis upward, and the plate lies in the xy plane, having displacement u and v, and thickness t. And for a given node here, we have the displacement w in the outer plane direction, and we have the rotations px and psy according to this notation. And these are some usual notations for the rotations that we will define. So if you look again, now the z direction is illustrated upwards. If we look in the xz plane, cut like so, we define the mid-surface position with a cross here, and we have out of plane displacement w, and we look at some point P here, which is located some distance z from the mid-surface plane. And we see how that point displaces under this loading. So this is the general case for thick plates. So we will have a rotation Cx, which will cause a displacement of these points in the x direction being minus z times Cx, given small angles of Cx. And you will have here the derivative of the displacement w with respect to x, which for thick plates is not necessarily the same as Cx, but in case of thin plates where you have no shear deformation, these values will be the same. So if I look at the point P and the displacement u, we have minus z times Cx. We will have the same in the other direction if we would cut the plane in the zy plane, but then Cy instead. We know from before that the strains are the derivatives of the displacements. So the derivative of Cx with respect to x and respect to y. And we will have the shear strains gamma xy following this strain displacement matrix, which is the same as we have studied before for plane elements. So we see that here epsilon x is the ddx of u, which we have here, and y, it's epsilon y is dy or ddv of y in this direction. So here we can see that the shear component gamma xy is a combination of the derivative of the u with respect to y and v with respect to x, which sums up to this expression. And similarly, we will have gamma xy, sorry, yz as a combination of the derivative of v with respect to z and w with respect to y. So we have w prim y minus c of y, and similar for the zx components. So the shear strains are, or all the strains are governed by this matrix. So that's the general expression for thick plates. And then we can reduce that for thin plates, saying that Cx is just the derivative of the displacement with respect to x, and the same in the y direction, and that we do not have any shear strains. Okay, so that's the kinematic equations. Now we go further to the constitutive equations, which describes the relation between the bending moments and the curvatures. So going back to the first slide here, we have this curvatures here, and we have the bending moments here, or the sectional forces rather. And here we have the constitutive matrix, which is in the general case the bending component or bending stiffness component, which is a 3x3 matrix, which is similar to what we had for the plane stress conditions. And we have another one that is the shear component in case of thick plates. So in this case, it will be a 5x5 matrix. And this curvatures are given by these equations here. So we have the second derivative of the displacements ending up with this curvatures here. So this describes the relation between the section forces and the curvatures. And if you look at small section of the element dx dy in the same coordinate system, subjected to some external load q here, and we look at the section forces for the general case of thick plates, we have bending moments mx and my, twisting moment mxy, and the shear forces qx and qy. And these section forces are obtained by integrating the stresses over the cross section. Whereas you have a linear variation in the bending stresses, and then you have this parabolic shape for the shear stresses. And if you have the thin plate theory, it reduces to only the bending component, so you don't have any shear components. so mx, my, and mxy. And the curvature is reduced to these components. And the plate stiffness here is similar to the flexural rigidity of a beam or a plate of thickness T in this case. So that's the constitutive equations. And then finally we go to the equilibrium equations. Again, we distinguish between the thick plates and thin plates. So we have the vertical load, and in this case, this picture is taken from the other literature, so the notations are slightly different. You note that here the load is described as Q and directed in a positive Z upwards, whereas now it's notated by P, and the Z direction is downwards. And I have omitted all the derivation of these equations, so that this is basic plate theories for looking at a small section dx dy. If we start with the thick plates, we have the derivative of the shear forces plus the external load in equilibrium. We have the same for the bending moments components in the x and the y direction. And in case of thick elements, you also have the shear forces and the torque load illustrated in this manner. So we have a torque load Qx acting like this, two directions. And this could be reduced for thin plate theory to this equation that we see here. Second order partial derivatives of the bending moments in the two directions and the twisting moments mxy. So similar to what I presented in a few slides ago. And all the section forces are described per unit length. So you have bending moments in, say, Newton meter per meter, and shear forces in newtons per meter. Okay, so then finally we assemble the differential equations using these different steps. So we start with the kinematic relations, over to the constitutive relations, and finally to the equilibrium equations. So this is I would say, the classical way of solving the plate equation. Obviously, you need to have boundary conditions to solve the differential equation. And I would say that only for very simple cases you have either closed form solutions or serious expansion for finding a solution. Maybe you have done that in some of the previous courses. To shorten the notations, we define the Laplace operator as follows. It's a set of second order derivatives like this. So then for the thin plate equation, we describe the differential equation as the second Laplace operator. This is noted del or nabla sometimes. And if you have thick plate equations, we have that component, but some additional terms, which is denoted with over here. It should say Cx there, I suppose. So those are the differential equations, but they are quite lengthy and difficult to solve in the general case. So then we would like to use finite elements to solve it. But before we go into that, another interesting distinction between the thin and thick plate theory, which is also important in the finite element context, is if we study section of pure twisting. So we would like to see the effect of the shear forces, shear stresses. So if we consider a plate with the length 2L here, so we have the origo in the center of the section, and we apply a twisting moment, a constant rate of twist in each end, mt here, and we have no other boundary conditions and free warping, so this is free to warp along the section. We will only have shear stresses in this case. And if you look at the mid cross section here, this is according to the theory of elasticity, you will have a constant shear flow like this along, or linear over the section like this. And if we have thick plate theory, you will have your twisting moment mxy along the section, which is constant in the section, and along the free edge it goes down to 0. And you will have the shear forces being 0 in the center and gradually going to its maximum value at the free edge. So this is what you would expect if you analyze this or describe this section with thick plate theory. In thin plate theory, on the other hand, we omit the shear strains, and the shear flow is represented instead of this twisting moment mxy, and you will obviously not have the shear strains in it, so it's represented by a discrete shear force at the end corners, which is denoted Q here. So you have a constant mxy along the section, and then for equilibrium you will need to have a shear force in the very end. This is also something that you will study in exercise A when you compare thick plates and thin plate theory, and look at the sectional forces at the free end. Okay, so now we come to the finite element formulation. So that the previous was more an introduction to plate theories. Do we have any questions so far? Okay, so I will just continue. So we start with a Kirchhoff plate element, which describes thin plates. And that we saw from plate theories is that it includes the curvature being the second order derivatives of the displacements. And when we solve this in a finite element context using the strain energy approach, we need to have a C1 continuity in the elements, just because the second derivatives of the displacements are included, so they need to be continuous. And the displacement field must contain a complete second order polynomial. So the general concept is the same as for other elements, but here we define the curvature as the second order derivatives. Prim here is the derivative, so this second order derivative of x and y and this xy. Similar to what we saw from the differential equations. So it's just the same as this Laplace operator. And this will form our B matrix, the strain displacement matrix, given the displacement vector D. And we define the strain energy as this integral kappa d times kappa integrate over the area. And finally, the stiffness matrix has the familiar form of B transpose D times B integrated over area, where the constitutive matrix D was previously known as the E matrix. So our focus will be on determining our B matrix for the different element formulations. One example is the four-noded Kirchhoff element. So I will show some examples on that, and then later I will show examples of a triangular element because it's easier to formulate, I suppose. There is a lot of different element formulations for plates, and usually what you would see in commercial softwares are shell elements, because you include the membrane components as well in the same element. So there are not so many pure plate elements, I imagine. But I will go through shell theory on the next lecture next week. So for now, we're only looking at the bending components. So this four-noded Kirchhoff element has 3 degrees of freedom per node point. So we have the outer plane displacement W and the rotations W prime in the X and the Y directions. So the shape functions is incomplete quartic, which is has 12 components like this. I will not show the full derivation of this element. I have some MATLAB code for it if someone would be interested, but I think we will focus more on the triangular element. This particular element has some deficiencies that it can only be integrated analytically for rectangular shapes, and it cannot really be generalized to non-rectangular shapes. Also, it has a problem of being incompatible in normal slopes, meaning that the derivative of the displacement may not be compatible over element edges. So this causes some numerical problems, but for smaller element sizes, this effect will normally reduces. The stiffness matrix here is defined as B transpose D times B, but then you have some geometric matrix defined like this. I will not go into detail about it. Defined by these parameters A and B, which are just coordinates. I will show some examples of implementing this in MATLAB, or the results rather. So if we have a square plate, in this case 5 by 5 meters, and apply some evenly distributed surface load on it, we can test these elements for different elementary cases. So the simplest one would be if we have 0 Poisson's ratio and 2 sides simply supported. So this will act as a beam. You will have the same example in exercise A, and you will see that if you have 0 Poisson's ratio, you will predict the same displacement using simple beam theory. So here is just a ratio of what this model gives compared to the theoretical results. If you have a non-zero value of the Poisson's ratio, you will have a transverse bending effect. So you will have a curvature in the opposite direction, causing section forces and stresses proportional to that Poisson's ratio. If we look at a cantilever beam, so it's a one-side clamped plate, slab, forcing boundary conditions for both displacement and rotations along this line. It will also fit very well with the theoretical values of just cantilever beam. If we have increased boundary conditions along the x axis on the edges, we will have one side clamped, and in this case, two sides simply supported slab. And here there are also theoretical equations for how to solve this. But using these current element formulations, we are underestimating the displacement using the finite element approach. So it's slightly over stiff compared to what this theory says. And lastly, if we have a four-side simply supported slab like this, there are also theoretical equations for how to solve that. Again, the numerical approach using the Kirchhoff element underestimates the displacements, so it's again a little bit overstiff. And the final case, if we have four-side clamped beam, so we also constrict the rotations at all of the sides, we have this displacement field instead. So these are some examples on how to test these elements. You can also try this using a commercial software, say Abaqus, to test the elements for known cases to see how well they perform. I think that we can have a 15-minute break now before I go into the discrete Kirchhoff triangle element. So I will just pause the recording, and if you have any questions, I can take those, and we will continue the lecture 10:10. Okay, so I will now continue with a triangular element. So previously we saw the four-noded Kirchhoff element, which had some deficiencies in only being able to have rectangular shapes, and some problems with incompatibility at normal slopes. There are many different kind of Kirchhoff elements, and in the early days, many of them suffered from different problems depending on how you define the polynomials and how the nodes and degrees of freedom were defined. I think one of the more stable elements is probably the discrete Kirchhoff triangle, which I will illustrate here. There's also a section in the course literature about this particular element, so you can read through that in a bit more detail for the purpose of better understanding. But it starts with a 6-node triangle as illustrated here. So we have in the XY plane and Z still being the out of plane direction. We start with the corner nodes 1, 2, 3, and then we have mid-side nodes 4, 5, and 6. It adds up to a total of 21 degrees of freedom because we have defined the rotations at all the nodes, but then also the autoplane displacements only at the corner nodes 1, 2, and 3. We use a complete quadratic polynomial to describe these elements, and the shape functions are similar to a plane triangle. I will show that on the next slide. As I said, the vertical displacements only define on element sides, and the slope is obtained by beam shape functions. So you will have similar to beam bending along the edges here, for instance. So we will illustrate briefly how the slope, say at node number 5, is defined using the beam shape functions. And after that, we will apply a set of constraints because the Kirchhoff element cannot take any shear strains. So applying those constraints, we can condense the element to 3-noded triangular elements, having 3 degrees of freedom at each node point, so the displacement and the rotations. So if you look at the shape functions, they are similar to what is described for the plane triangular elements in chapter 7 in the book. Interpolation functions, we have 6 of those for the 6-noded elements. Similar as before, it has the value 1 in its point. So if you have n1 in this coordinate 0, 0, you will have the value 1, and at all the other nodes you will have 0, and etc. So the rotation components are interpolated from the nodal rotations Cx, I, and Cy, according to this summation here, using this 6-node elements. And if you look at one of the edges of the element, say from node number 2 to 3, which was described over here. So take this part of the picture from node number 2 to node number 3. This is described, the mid node number 5 here, the slope of that is described using the shape functions for beam bending, which we also find in a previous chapter in the book. And by differentiating those, rearranging that, and solving it at the midpoint, we will end up with this expression. So it's a function of the displacement at the autoplane displacement at node 2 and node 3, and the slopes at node 2 and node 3, W'(S2) and W'(S3). And doing the same thing for the other edges. Then we would apply some constraints. We have no shear strains in the Kirchhoff element, so the shear strain components will vanish at the corner nodes. Similar to what we defined in the beginning, the slope is defined as the derivative of the vertical displacements for all of the corner nodes. And similar, the shear strains also vanish at the mid sides. So the corner nodes 1, 2, 3, and the mid sides 4, 5, and 6. And then the normal slopes very linearly along each side as described here. So the end direction is the normal slopes. There are more detailed description in one of the chapters in the book if you're interested in knowing more details how to obtain this derivations. In the end, we can condense this to a 3-noded element having 9 degrees of freedom, where the strain displacement matrix is defined by differentiating the shape functions. This triangular element will have some arbitrary position in the xy plane, so we need to have a transformation matrix to transform it into the global coordinate system. And here is the displacement vector. So I will not show in detail how this B matrix looks like, but it's a function of these shape functions and these constraints that we apply. And then the usual expression for the K matrix is B transpose D times B for this element. In the book, there's also some examples on the accuracy of this element. So it's quite versatile in the sense that you can model any given geometry with this triangular element. So you can assemble square sections as a combination of these triangular elements. In this case, we have a center line here. We have an evenly distributed load, I believe, in this specific example. And we compare different results, namely here at the center point, the vertical displacement at point C, and the bending moment at point C. And only using this many elements, we generally obtain very good accuracy compared to theoretical results, as we can see in this figure. Of course, if you have clamped conditions, we would need more elements to describe the curvature in a proper way. So we have some 20 or 30% difference between the theoretical solution and the numerical solution. There are some tricks about having overlapped elements in order to improve the quality of the solution. I'm not going into much detail about that. So that was some description of Kirchhoff elements. Usually in most finite element softwares, the default element type would be the Mindlin plate element, which also considers shear deformations. And more generally, it also includes the membrane components, them being a complete shell element. But here we will only look at the plate components of the Mindlin element. It's the derivation is somewhat more difficult. It could be considered as a special form of isoperimetric 3D solid elements. Solid elements only have translational degrees of freedom, but they are also defined through the thickness direction, which is can be considered as an extension of the 2D plane stress problem. And then we can also describe it using the thick plate theory, including transverse shear deformation. So there are different formulations for the Mindlin elements. Similar to Timoshenko beam theory, the Mindlin plate element only needs to be C0, have C0 continuity. And we can use a complete first order polynomial to describe the elements. Some deficiencies is that it has a risk of shear locking if the element is very thin. I will show some examples of that. So again, we start with looking at four-noded plate element, set direction in the positive upward, same degrees of freedom, out of plane displacement W, and rotations Cx and Cy. And we can use the same shape functions as for plane elements. So this is the bilinear four-noded elements shape functions. Here defined in Xiata, as we saw from the previous lecture for isoparametric formulations. We have the curvature vector kappa, which these components we defined in the theory part in the beginning of this lecture. So we have the curvature in the x and y direction, twisting component, and then we have these shear strength components, which is now non-zero. And previously also defined the B matrix as the derivative of the shape functions. This is the resulting B matrix of the Mindlin plate element, where the derivative is the set of first order derivatives, which I don't give in expansion here, but the resulting B matrix is something like this. We also have the internal strain energy, similar as before, from which we can get the stiffness matrix as an integral of the strain displacement matrix B as B transform D times B. Now the constitutive matrix is a 5x5 matrix, where the first 3x3 components is the bending, and the last 2x2 diagonal is the shear component. In short, we can separate the bending and the shear components because we can see here that they are uncoupled for this type of element. And this is a good thing because for different numerical reasons, we would like to have different integration order of the bending component and the shear component to avoid the shear locking effects. So for the general case, using isoparametric formulations, we will resign to numerical integration to determine the stiffness matrix in a similar fashion that I showed on previous lecture for isoparametric formulations. So we have the component, index B stands for bending and index S stands for shear. So I will illustrate a little bit about the effect of shear locking in the Mindlin plate elements. This is also taken from the book. We have different scenarios. We have a state of pure bending and pure twist, and then in that case, the bending stiffness component is correctly evaluated. So we have constant bending, like this picture illustrates. And if you look at bilinear element, it will deform something like this because we don't have we have a bilinear formulation, so obviously it cannot really bend properly. And we have a problem with the shear strains. But if you use 1 point Gauss quadrature, we see that the implied versus actual shear strains has the same value using a 1 point Gauss quadrature in the center of the element. So that could be used to avoid shear locking. And this is similar to what you obtain in a four-noded bilinear plane elements, which is also prone to shear locking. If you use a 2x2 Gauss quadrature, the bending stiffness component is overestimated by this factor. So for smaller thicknesses, this value will increase. Linear variation in bending always overestimate the shear strain in beam elements. If you look at second order elements, the quadratic one, we have a better, actually perfect estimation of the shear strains for the pure bending case. And we will have similar problems here for the twisting components. But if we use reduced integration being a 2x2 Gauss quadrature, we can see that at this Gauss points, we also have an exact solution compared to the actual ones. So similar for a second order Mindlin element, if you use reduced Gauss quadrature, we can also improve the shear locking effects. Here's another example from the book where we have increased ratio of span length over element thickness. So we have increasingly thinner plates for increasing values here, going to somewhat extreme values here. And this is illustrated for a case of a uniformly loaded square plate and different integration orders for the shear components and the bending components. Whereas what is denoted in this table as selected integration is that you have a lower order for the shear integration for reasons that was illustrated over here to avoid shear locking, basically. So we have full integration denoted by F and reduced by R and selective by S. And on the y-axis here, we have the ratio between the computed and the theoretical vertical displacement. So if we start with a bilinear four-noded plate element, we will have, using full integration, a lower value of the computed displacement compared to the theoretical ones. So it behaves somewhat overstiff. But if we have a reduced integration or a selective integration, we will have an improved behavior. So if we have a 2x2 integration still being the full integration for bending, but 1 point Gauss quadrature for the shear component, it will behave fairly well for the bilinear element. If we go to higher order elements, we have the 8-noded serendipity element and the 9-noded Lagrange element. Similar definitions as we saw for the higher order plane elements. And if you have full integration for, say, the Lagrange 9-noded element, we also have slightly overstiff behavior over here. And the 8-noded elements perform somewhat worse down here. But if you have reduced or selective integration, we have a great improvement of the element. So the higher order element with reduced or selective integration order performs quite well in this case. There is some potential divergence for these higher order elements over here. This is described more in the textbook, but maybe not a very practical issue. It's more for benchmarking the elements. So generally speaking, second order plate elements perform better than the first order ones. But one should be careful about which integration order to use, because if you use a full integration order, you may have overstiff behavior due to shear locking. So that's quite important when you use any commercial software, that you know what kind of element formulation you are using. I will show that a little bit, how that is defined in Abaqus and where you find the different elements, because part of exercise A is for you to compare different element formulations with each other. And there are different places in Abaqus where that is defined. So that's actually the main part of today's lecture when it comes to plate theory. Do we have any questions so far? No questions so far. So the whole lecture here is kind of an overview to part of chapter 15 in the book. So if you have more interest in plate elements, I advise you to read more in the book about that. Also, this other book about plates and FEM is quite good for understanding different applications of using plate elements in finite element approaches, and different kind of things that may go wrong in analysis. So hopefully today you have get some insight in the differences between the Kirchhoff and the plate theory, Kirchhoff and Mindlin plate theories for plate bending. So I will now go into some explanation about how to use Abaqus. Typically, we don't give that large, extensive introduction to Abaqus, but I think today we have some extra time, so I can do that and maybe point out some things that usually goes wrong. So emphasis on that. There are many different kind of commercial finite element softwares which do pretty much the same thing. But in this course, we're using, at least for this part, Abaqus, which was developed in the late 1970s. It can deal with all kind of linear and nonlinear analysis, statics and dynamics, and multiphysics. And in part A, we will only deal with linear analysis and also statics throughout this course. So very simple analysis. Much of it could have been done using scripting in MATLAB also, but the more complicated the geometry you have and the more degrees of freedom you need to manage, it tends to be more difficult to use it by writing your own code, and more convenient to use a graphical interface to generate a model. But still, I believe it's important to understand the background theory on the different element formulations. So you could very well make a very complicated model without any prior understanding of how finite element, the finite element method works. But our intention in this course is to use the commercial software as a tool to understand the element formulations rather than doing advanced modeling. I put up some additional explanation on Canvas on how to install it. So you can, there's another license document link through the link I sent. So it's a very extensive manual of tens of thousands of pages on everything from the background theory on different element formulations to how to do modeling and stuff in Abacus. So if there's anything you can't find in our tutorial, you can go either to the manual or you will find a lot of tutorials online on other places. And you will use this to solve part 3 of exercise A with plate and shell element problems. I will go through shell element theory next week, but you can get started with modeling in Abacus before that. Also exercise B, which will be given by Romain on pavement structures, will be solved using Abacus. I guess that some of you also are taking the course in concrete structures, AF 2102, I think it's still named like that, which I believe you will also be using Abacus. In that course, I think you are using nonlinear material formulations, which is not covered in this course. But you can use the same tutorial if you would like to understand something about modeling aspects. So some short introduction to the structure of Abacus. It's built up of different modules. You have a part module where you create the geometry of each individual component of your structure. Throughout the exercise A, you will only have one part, being one slab, basically. Also, in the last part where you do the box girder bridge, you will create that as one single part. But generally, you may have different kind of parts that you later need to assemble to a global structure. Each part will, in the property module, be assigned different material properties. I will show later in detail that. Then in the assembly model, you just assemble the different components in their correct geometrical space. So still they're not connected to each other. They're just assembled to their correct global geometric position. In the step module, you will select the type of analysis. In this course, we will use static analysis. You can also do nonlinear analysis. You can do dynamic analysis, eigenvalue analysis, and other kind of substructuring analysis. In the interaction model, here is where you connect the different parts that you may have defined in your assembly. So you assign constraints and contact conditions in between the different parts. And then you have a separate module for applying loads and boundary conditions. So you can have loads or prescribed displacements, prescribed dynamic conditions, different kind of boundary conditions, and so And up until this point, your model is not really a finite element model. It's more like a geometric model with different properties, similar to what you would have obtained using a CAD program of any kind. It also has some support for importing geometries from other softwares. But when you come to the mesh module, here is the important part for discretizing your model, your geometrical model, into a finite element model, and also defining different element types, the order of elements and the type of elements. And there are different menus in how to select that in the mesh module, but it depends on how you have defined your elements from the very beginning. So some of that is defined already in the part module, where you design on the model space of the elements, and in the property module on the part of the element formulations. And then there is a separate module for running the analysis, just administrating different simulations. And here, when you run the analysis, you can also look at the results if anything goes wrong in the analysis. If you have modeled something in an improper way, Abaqus may give a warning about that. For instance, if you have a too deformed mesh, that may cause problems when doing the numerical integration using the Gauss quadrature, as you may remember from the last lecture about having distorted elements and how that may affect the accuracy of the results. So you may have a lot of warnings in this, but you may still be able to run the analysis. It also gives you an error if something is defined in an inappropriate way, such that you cannot solve the system. And when you run this analysis, the graphical interface calls for a command prompt command, which runs basically a text file to run the analysis. And then you can open the resulting result file in the visualization module, where you can view and post-process the results. I think I actually have time to go through the full tutorial, but here is an example of how you can define elements in different modules. So, for instance, in the part module, we may define planar shell elements in 3 dimensions. In the property module, we have additional choices to have a homogeneous or composite or main membrane element or other formulations using shell elements. So I don't think there is any menu saying only plate elements. So you will be looking for shell elements, which is a combination of plate bending and membrane stiffness. And then in the mesh module, you have also different formulations for the shell elements. You may have the linear or quadratic elements. Depending on what kind of mesh you will assign, you will have different formulations also. So here, if you have a quadratic mesh, you may have a 4-noded element denoted S4. If you click on quadratic here, you will have a second order element formulation. So the shell elements, as I said, was a combination of plate and membrane actions. We have 2 different element formulations, the Kirchhoff and the Mindlin elements, in which the Kirchhoff element is only, to my knowledge, defined by the triangular element. So the default element in Abaqus would be the Mindlin element. So you need to go in, have a triangular mesh, and select STRI3 in order to find the Kirchhoff element. And the S3 element is a similar triangular element, but using Mindlin plate theory. And then we have the quadrilaterals, which are 4 or 8 noded elements. And all of them are general purpose thick shell theory, also using Mindlin theory. One thing that may be quite useful is the notations of the section forces. By default, you will not be able to extract section forces at all in Abaqus. You need to go into the step module to change the outputs. So I'll show how that is done. And when you have done that, you will have the section forces component defined SF1 to SF6, and the bending moments SM1, 2, and 3. And looking at the general shell element, which have the shear forces and bending moment components for the Mindlin element, and also the membrane action being the NXX and NXY and XY are organized according to this scheme here. So when you're extracting, say, your bending moment MXX, you need to look at this component SM1. And then also assure what is the X and Y direction in your model, obviously. So that's the end of this presentation. I think that we may just continue, and I can give a presentation of Abaqus. I don't think it will take more than, say, 20 minutes or so. So if no one is complaining, we can continue to do this without a break, perhaps. And then we can finish a bit earlier, and if anyone have questions, I will be available to answer questions either related to the lectures or to the exercises. So this introduction to Abaqus is available on Canvas. It's relatively self-explained, but since we don't have the in-class exercises, I will try to go through this a little bit more so that you don't miss anything that are from previous years, typical things that you may not think of. I can show some of the tutorials. We have the cantilever beam using plane elements, and then we have the square plate using shell elements. So the second tutorial is pretty much the same as you will be doing in part of your exercise A. And the last part is how to extract beam section forces from general models, which you will be doing in the very end of exercise A for the box girder bridge. I can skip this because we already got through that. This is where you find Abaqus if you would be in the computer room at KTH, but after you install it yourself, I imagine you will find it. And hopefully you will be able to connect to the license server at KTH. This illustration is for a later version, earlier version of Abaqus, but it's not a very big difference compared to the newer version, at least not for our applications. So the CIE stands for the graphical interface. You can also run Abaqus directly from a command prompt, and it also have support for using Python scripting, which could be used either for or both for just generating the whole complete model or for extracting output results. I have not included any tutorials on how to do the Python scripting in Abaqus, but if any of you have previous knowledge of writing code in Python, there is a whole tutorial or sort of a whole manual on that in Abacus on how to make models and also how to extract data from the result file. So if you have larger systems or want to do a large parametric study, it could be convenient to make such an approach. But in this course, we will do everything by default in the graphical interface. This is the layout that you will see. You will have here the different modules that I talked about previously. So in this list, you will find the different modules, and every time you go to the new module, all these buttons and interface will change to suit that module. You also have a tree structure on the left where you can find all of these things in between the different modules. You have the parts and the assembly and so on. And then you have a command line area down here from which you can see what's going on in the module, or you can also call for different kind of Python scripts directly in this message area. And if you have any problems on how to define things, if you're in a certain menu, you can often just press F1 and you will automatically go to the corresponding part in the online manual. This is just some recommended graphical settings, because when you extract results from your model and put in the report, it's good if you say, for instance, don't have a black background or stuff like that. So it's just to clean up the output, sort of. You can also just use a copy-paste function to copy the model, the screen in the module. I don't think there's so much relevance here. Maybe that the model file is saved as a CAE file, which is the model file of your geometry and all your definitions. So that's the important file to save. Every time you run a job, it will generate an input file. And this is just a plain text file defining the geometry, type of analysis, elements, and so on, which is interpreted by the finite element solver. So this is actually what creates the finite element model. And then, if successfully, it will create an output database with a result file named as ODB. But you can always rerun the ODB file if you have either the CIE file or the input file. So it's important to save at least the CIE file if you want to replicate the results. And you have a dat file and a message file, which includes some analysis or log of how the analysis is proceeding. If there's any error or warning messages, you will find it in either the dat file or the message file. So let's go through the simple cantilever beam example. So this is the same model that you will model using plain elements in MATLAB. But this exercise is illustrating how you do this exact same thing using Abacus. So you start with a part module to create a 2D planar, what is here called shell. So shell is kind of a generic definition. It doesn't include any plate bending, but here it's only the membrane component, which you will know as plain elements. I will have it in the 2D space. And then you will have kind of a sketch module where you just draw the geometry. similar to any kind of CAD system. So to define the length and the height of the beam using these different tools here. Then it will look something like this. So this is the main part that you will have. You can also follow this in this tree here. So you see here that you have one part right now being this one. You then go to the property module to define the material properties. Here is how we do that. You go to material and create, and you get this menu over here. And there are different sub-menus in order to define different varieties of material. But here we are using only a linear elastic material of a certain Young's modulus, and in this case, a 0 Poisson's ratio. So now you have defined a material, but then you need to define a section as well. So this is the general procedure for assigning materials to a part. So you define a section being a solid homogeneous. So now it's not shell, but it's solid homogeneous. So that's important to keep track of. And then you have another menu called Edit Section, where you define the thickness to the structure. So the thickness is assigned using the material of the elements and not in the part module. So we have a 0.1 unit thickness. And then we have the Edit Section assignment module, which is the last one. So all these steps is needed to be done in order to define the material. And then we assign that to this cantilever beam. So then we go to the assembly module, and we insert this part, which we now call beam, for instance. And then we will have one part in the assembly module. We don't need to do anything extra with that. Then we go to the step module where we define the analysis. So we select step and create to create a static general analysis. There are many other options that we will not bother about in this course, at least not in part A. We don't need to do any special settings here. Here is an option if you want to have a geometric nonlinearity to account for second order effects, which we'll not do in here. And if we would like to store section forces as the output, we need to go to this menu called Output Field Output Requests. I think I will show that on the slab model later. But for now we just do the defined outputs. We apply loads in the load module, in this case on the top line over here. We have a magnitude of 1,600 kilonewtons per meter uniformly along the top surface, and that is defined as a pressure load. And yeah, be aware that the pressure load is defined per area. So we have a certain thickness in this one. We go to the load module to define our boundary conditions. Sorry, we're still in the load module, but we need to define the boundary conditions. So on the left side, we have the X and Y directions, which in Abaqus are called 1, 2, and 3. So X being 1, U2, and Z3. So we have the displacement U1 and U2, which we constrain along this edge. Plane elements doesn't have any rotational degrees of freedom, so we don't need to define that. And then we go to the mesh module, So still we only have CAD geometry without any discretization, because that is obtained here in the mesh module. And then we need to select the number of elements, which in Abaqus is called seeding. So the seed is the number of node points along different edges. And in the MATLAB script, you will define the number of elements in the X and the Y direction. Whereas here you can assign a global mesh size, say of 1 meter. You can also define certain element divisions along different edges if you would prefer to do that, which is useful if you want to design your mesh a little bit more in detail, not having this general meshing control. So after I apply the mesh, now it looks like finite element model. And we need to define the type of elements to be used. We have here rectangular elements, and then we use plane stress analysis, linear first order elements, which are called CPS4 in this case, which is a 4-node bilinear plane stress quadrilateral. If you have the second order, you will go to the quadratic element there. So now we have defined the structured element mesh, the loads and boundary conditions. So now we're ready to create a job. So we go to the job module to run the analysis. So we do that by creating a job, and depending on your definition when you install the program on your home computer, this may not be the default directory. But you will find that under this job create menu, which is called a scratch directory. So this is where you can retrieve all the results file afterwards. And then you have this menu where you can have many different kind of jobs, and you can run those, clicking on submit, and hopefully it will have a status of completed if everything goes well. And then you click on results to see the output results, and then that will get you directly to the visualization module. So this is an illustration of this cantilever beam showing the von Mises stresses. So obviously we have the largest stresses at the clamped end of the cantilever beam. So there are different options in the mesh module just to have contour plots and illustrating the deformation of the system. We can also use, by default, you have a nodal averaging. Or first we will look at different components. So the S11 component is the longitudinal stresses, because X is in our model defined along the beam. So if you go to this field output menu and we select the S11 component, we have the longitudinal stresses. This is using nodal averaging, so you have a rather smooth stress field. You can go to this option to not use the averaging by unclicking this box here. And then you will have a discontinuous stress field over the element boundaries. Because the plane elements have a continuous displacement field, but a discontinuous strain and displacement, strain and stress field. Let's see. Can you still see my screen, by the way? Or am I? Let me see. Can everyone see my screen?
Yeah, we can see it.
Okay, great. I thought it was some sort of bounding box there, but yeah, okay. I was afraid it was just talking blindly for a long period of time, but that's good. Yes, so this is about averaging of stresses. Also, what you would like to do is extracting results along different result lines, which you can do by defining a path. So you go to tool path and create. You can make a node list, for instance. Typically, you don't know the node numbers of your global structure because it's automatically generated by the program. If you do it in, say, MATLAB, you have more control or more knowledge about the different node numbers, I suppose. You can visualize that in a model, but actually with this one, you only need to know the start and the end point, and you can click on that in the program, and then you can interpolate the results along that line. Typically, you would like to do that for the undeformed shape. So in order to do that, you will have this menu for the data extraction. You select the extract results along, say, the x coordinate, if in this case the structure goes along the x direction. And you need to click in this box which says include intersections and do that on the undeformed shape. And then Abaqus will find the intersecting points along the top surface in this case. So instead of, So instead of defining all the intermediate points here, just define the start and the end points. So that this is the same procedure that you will do for the slab exercise. Then you can extract the data either by a graphical plot directly, but preferably more to a data list like this. And I think that the plotting functions for plotting XY graphs in Abaqus is maybe not so great. So I would recommend that you extract the data and plot it in another program, say Excel or MATLAB, in order to assemble it in a proper way. You can do it in Abaqus also, but I don't think it's worth the time. Okay, so you also select here the different kind of field outputs, which now is defined as S11. And this is some option for extracting averaging results. So if you unclick the average element output at nodes, then this will not be averaged. You can also extract results at specific nodes. Now we only have one solution steps. So you will only have, well, by default you have step 1 is just the initial state of node displacements. But if you go to ODB, field output, select unique nodal, and in this case, the vertical directions is the U2 direction for displacements. So you select these components, click on the element nodes tab, and you can select from the viewport clicking on, say, this node in order to select to extract data from that node. You can also create node sets that are previously predefined in your model, not needing to click on the specific nodes in a model. And then the result will be this simple table that you only have one solution step with one displacement being this value. If you have more solution steps in other analysis, you'll have a longer list here with sort of a time history result. So you can extract results in different ways. One is you have a menu called Report XY Data, where you select data that you have extracted through the model, and you can store that to a result file, which you define in this menu. and then it will create just a text file which you can read directly by any software, or you can generate it in such a way that you extract it directly to Excel. So there is some functionality in Abacus to extract data directly to Excel. So you go to the menu, plugins, tools, Excel utilities. So it's a matter of finding the most convenient way of extracting data. Maybe many of you would prefer this way. And it's preferable if you, in the final report for exercise A, sort of clean up the pictures, clean up the graphs a little bit, so you don't have hundreds of these graphs. But if there are things that you can present in the same plot, you can. I prefer if you spend some time in organizing the data in a proper way. And also think about what kind of units you are presenting the results in. And the resulting file from the analysis, Abacus will generate a number of files in the Scratch directory. Not all of these are of great interest for you. It's more things that are done during the analysis. And if you are a more advanced user, you may have interest in some of the files. But the important file is the CIE, which is the model file, and the ODB file is the result file. So every time you rerun a job, most of these files will be replaced with a new analysis if you have it with the same name. I think I can go through the square plate example also without any break. I think it'll go fairly quick, and then after that I can answer some questions. So this is actually the same slab that you will have in part of exercise A. In this case, it's let's see what boundary conditions here. It seems that you have simply supported on 4 edges, so slab number B. Let's see if it was the one I analyzed. Same procedure as for the plane element. For the cantilever beams, you make the model in the part module. Here you define the material properties in the property module. But now, since we have a plate element, we will go to the shell element tab, select homogeneous, and then we have another definition for the element thickness in this menu. So the edit section menu here for shell elements look different compared to plate elements. We can select different integration rules. And in the edit section assignment module, we usually define the thickness by its mid surface, but you may have an offset of that also in this menu. We go to the assembly module, just insert our only part, which being this slab. You may, if you want, assemble 3 slabs which correspond to problem A, B, and C, I think they're called in exercise A. But it's better to do them separately, because if you include them all and do the analysis of all of it, your system of equation will be much bigger. It doesn't have much practical problem for you now, as long as you can use the KTH license. But if you're restricted to 1,000 nodes, you should do it one slab at a time. Here is an important part to consider for the slab exercise, that by default, you will not have any output in terms of section forces. So you need to go to the step module and to the edit field output requests. And under this list here, identify forces and reactions and tick the box with section forces and moments. When you do that, then you will be able to extract section forces. So this is important. In the load module, you will define a pressure on the surface. In Abaqus, they distinguish between the top and bottom sides by different colors denoted here. I think that the only definition is the orientation of the load. So you should preferably have it from the top side, and then a positive pressure will end up with having a downward loading. I imagine that if you define the opposite side being the lower side, the force will be directed in the other direction. And then you can do that either by switching the surfaces or switching the sign of the load. For slab 2, we assign the boundary conditions as being simply supported along each of the 4 edges. So now we have the displacements, global displacements x, y, and z as u1, 2, and 3. We don't want to restrict any rotations, which otherwise are denoted ur, 1, 2, and 3. We go to the mesh module, and we have different options for elements. By default, we have the thick shell theory for 4-noded. I think that by default, it might be the reduced integration element. But you can tick this box if you want to have, or untick it if you want to have reduced or not reduced integration. And here you define, say, mesh size. So something about Kirchhoff elements, they only exist to my knowledge in Abaqus using triangular elements, STRI3. So when you assign the mesh control, by default, you will probably have a quadrilateral elements, but you need to go into the mesh control, define triangular elements, and mesh it with triangular elements. I don't have the illustration of that. And first then, when you go to the element type menu, you can select this linear small strain element, which is the Kirchhoff. And then it will says in this tab here, STRI3, and then you know that you have the correct element. So this is the procedure in to find this element. So if you have only the S3 elements, then it's the Mindling counterpart of the same element type, or geometrical type rather. And this is the procedure in how to find that. If you go to the visualization module after completing the analysis, you have a definition of the stresses. Now you're not really looking at the stresses in this example, but rather the section forces, which are defined in relation to the mid-surface. But if you are interested in stresses, you can select to have it either on the bottom or the top surface, or both, or an envelope of it. Preferably you can tick the box of having both top and bottom, because then if you rotate on the model, you will see different stresses on the top and bottom sides. And by convention here, infinite element programs in Abaqus especially, compressive stresses are defined as negative and tension stresses as positive. I showed this picture before about the notations of the section forces in different directions, so I don't need to go through that again. But this is important for solving the slab part of exercise A, in order so that you know that you get the correct components. And the very last slide deals with how to extract beam section forces from general models. And this is the very last part of exercise A, where you model the box girder bridge. And this is part of that bridge. And there is a facility in Abaqus in which you can integrate the stresses over the cross section in order to get the equivalent beam section forces, which is illustrated by these red and blue arrows. So these are the shear forces in the different directions, and these are the bending moments and twisting moments in different directions. And the values here is the extracted or the integrated value of those entities. So there's a procedure here on how to find that. It's called free body cut in Abaqus. So you can retrieve resulting beam section forces using either plane or shell elements. I think you can also do it for solid elements. But what it does, it's integrating the stresses in your model. So if you have any stress concentration or local defects in your model causing unwanted stress concentration, that will be included in the integration. So you may have rather spurious results in those regions, especially say at support conditions if you model those in an inappropriate way or have other kind of stress concentrations. Also, what is important to know is that you should extract the results based on the undeformed shape, which is noted here, because if you do it from the deformed shape, there might be some error in Abaqus, because it, for some reason, integrate the stresses based on the deformed shape, which seems to be the deformed shape illustrated in the visualization module. So be sure to use the undeformed shape when extracting that. And then you will have all these components, which you can, in this exercise, compare to simple beam theory results. Also, in the free body plot option menu, you should select components. Otherwise, you will only have one resulting force and moment pointing in the resulting direction of these three. But you would like to see the different force components using this option. So that was actually the end of today's lecture. We kind of skipped one of the breaks there. I hope you're still awake. But I can now stop the recording and I can answer some questions.